Welcome to month 2 of the Senior QA Engineer track at Bistec Hearts Academy. This session is called Test Automation at Scale, a 4-hour workshop covering how to design pipelines that run tens of thousands of tests fast, reliably, and cheaply. We'll move through CI/CD test integration, parallel execution with intelligent sharding, flaky test detection and quarantine, and test impact analysis. By the end, you'll have a concrete orchestration design that targets 10,000 tests in under 30 minutes. Here's the shape of the day. 4 hours, 4 distinct blocks. The first hour covers CI/CD test integration, how to stage tests by risk and runtime, so that every pull request gets feedback in under 5 minutes. The second hour goes deep on parallel execution, sharding strategies, load balancing, the trade-offs between worker count and cost. Hour 3 is the hands-on block. You'll build a working slice of a test orchestration system. And in hour 4, we look at flaky test detection, review your orchestration designs, and close with a retrospective. The goal for the session is a design that is production credible, one you could hand off to your team and start implementing this week. By the end of this session, you'll be able to do 5 specific things. First, design intelligent CI/CD pipelines that stage tests by risk and runtime so PR feedback stays under 5 minutes. Second, implement parallel execution at scale, sharding tests across workers with balanced load and predictable cost. Third, build a flaky test detection system with statistical scoring, automated quarantine, and a structured path back to the main suite. Fourth, apply test impact analysis to run only the tests that a code change can actually affect. And fifth, cut total execution time by 70% or more, going from 4-hour test suites to under 30 minutes, with the metrics to prove it. The foundation of fast, reliable testing in CI is the right stage strategy. Think of it as 5 concentric rings. The innermost ring is lint and unit tests, 5,000 tests, triggered on every push, capped at 5 minutes. These protect compile correctness, types, contracts, and pure logic. The next ring is integration tests, 500 tests, also on every push, capped at 10 minutes. These verify service boundaries, real databases, and queue interactions. Then smoke end-to-end tests, 100 tests on every pull request, 5-minute cap, covering the critical paths through the live UI. Behind merge to main, you run the full end-to-end suite. 5,000 tests across all browsers, 30 minutes. And the outermost ring is the nightly regression suite, 10,000 tests, 60 minutes, scheduled for 2 in the morning, so results are waiting when the team arrives at stand-up. The key principle here is the PR contract. Never block a merge for more than 5 minutes of feedback. Push the heavy, slow, and broad checks behind merge. That keeps review velocity high and engineers unblocked. Here's what this looks like as a concrete pipeline. The first job is lint and unit, with a 10-minute timeout. The integration job declares a dependency on lint and unit, using the needs keyword, and spins up a Postgres service container. The end-to-end job depends on integration and fans out across 8 shards using a matrix strategy. Each shard runs 1/8 of the suite in parallel. Finally, a merge reports job runs unconditionally using the always condition. 3 design decisions worth highlighting. Setting fail fast to false means one shard failing doesn't cancel the other 7. You still get partial results from the healthy shards. The needs chains mean stage 2 and 3 only run if stage 1 is green, saving CI minutes on obvious failures. The unconditional report merge means you can debug failures even when the suite is red. And the nightly cron at 2 in the morning runs the full regression suite, so results are ready before stand-up, not during it. Parallelism is the biggest lever you have on wall clock time. Here's the intuition. If you have tests that take 8, 3, 2, 1, and 1 minute respectively. In serial, that's 15 minutes. Distribute them across 2 workers with the 8-minute test on worker 1 and the rest on worker 2, and your wall time drops to 8 minutes. You've cut execution time nearly in half with no changes to the tests themselves. 3 things make parallel execution work in practice. First, greedy bin packing. Sort tests by historical runtime descending, then drop each test onto the worker with the lowest current total. This keeps variance under 10%. Second, understand the cost trade-off. Doubling workers halves wall time, but doubles peak CI cost. The sweet spot is determined by your slowest single test. That's the floor you can't go below. Third, and most often overlooked, test isolation. Shared database rows, file paths, and ports all break parallel runs. Every worker needs its own isolated fixtures. There are 4 sharding strategies to know, each with a different trade-off. File-based sharding splits test files evenly across workers by count. It's the easiest to set up and works for small suites, but it produces poor balance. One long test file can dominate a worker. Time-based sharding uses historical runtime data and greedy assignment to the least loaded worker. It's the default for most teams and delivers excellent balance, under 10% variance. Tag-based sharding groups tests by metadata tags like checkout, auth, or search. The balance depends on how your tags are distributed, but it maps well to team ownership boundaries. Impact-based sharding is the highest payoff strategy for pull request pipelines. Map code coverage to tests, identify which tests can be affected by a given change, and only run those. On an average pull request, this produces an 80% reduction in test count. In production, these strategies are combined. Most mature teams use impact-based selection on pull requests to shrink the test set, then time-based sharding to distribute that smaller set optimally across workers. The orchestrator is the engine that drives all of this. Think of it as a contract with 4 methods. Analyze reads test history, runtime statistics, dependencies, and ownership tags to build a picture of the test suite. Create shards applies a pluggable sharding strategy, time-based by default, but swappable, and returns a set of balanced shards. Execute dispatches shards to workers, reports progress in real time, and persists partial results so a single worker crash doesn't lose the other worker's output. And merge combines shard results into a single report, surfacing any tests that required retries. The pluggable sharding strategy is the key design choice here. Because the strategy is an interface, you can swap file-based for time-based for impact-based without changing the orchestrator. That's the extension point that makes this architecture last as your suite grows. Here's the concrete implementation of time-based sharding. The algorithm is 3 steps. Sort tests by average duration descending, longest first. Create an array of empty bins, 1 per worker. Then for each test, find the bin with the lowest current total and assign the test to it. Why does this work so well? The sort is order n log n, and the assignment is order n times k, where k is the worker count. Trivial at 10,000 tests. The longest first ordering is the LPT heuristic, which is provably within 4/3 of optimal balance. Historical average duration comes from your test reporter. A rolling 30-day mean works well. And for new tests that have no history, assign the median runtime of existing tests so they don't accidentally starve one worker while all others wait. A flaky test is one that produces different outcomes, pass or fail, across runs on the same code. The detection algorithm works by analyzing the last 30 runs of a test, calculate the pass rate. If the rate is above 10% and below 90%, the test is flaky. It passes sometimes and fails sometimes. A pass rate near 0 or near 1 is a reliably passing or reliably failing test, which is a different problem. Beyond the binary classification, you calculate a flakiness score between 0 and 1 based on result variance. A higher score means more unpredictable behavior and higher priority for investigation. The telltale signals to look for. Toggling outcomes. The same test alternating pass and fail on the same commit. Pass on retry patterns. Fails first, passes second, which usually indicates a timing or isolation bug. Worker correlation. Always failing on shard 3 but not shard 1, which points to resource contention rather than a test logic bug. And high variance in runtime. A test whose execution time bounces by 5 times between runs is often a flake in waiting. Once a test is detected as flaky, it goes through a structured lifecycle rather than being ignored or deleted. The lifecycle has 4 states. Active is the goal state. The test runs in the main suite and blocks merges on failure. Quarantined means the test runs in a separate parallel job. Results are visible and tracked, but the test cannot block a merge. This is where flaky tests live, while they're being investigated or fixed. Disabled means the test is skipped entirely, with an automatic ticket filed against the owner and a requirement to document the root cause before it can be re-enabled. Fixed is a probation period. The test returns to the main suite with a probation tag, and if it flakes again, it's automatically re-quarantined. After 20 consecutive passes in the main suite, without a flake, it graduates fully back to active. This life cycle is important because it's the difference between muting a problem and managing it. A quarantine test is still visible, still tracked, and its owner is still accountable. The flaky test dashboard makes the cost of flakiness visible to the people who can fix it. At the top level you see aggregate health, total tests, how many are flaky, how many are quarantined, and how many were fixed this week. Below that is a triage queue ordered by flakiness score. The tests most deserving of attention right now. 3 things make this dashboard earn its place. Visible cost. Owners can see their flakes, so ignoring them is no longer free. Trends, not snats. A test that's been flaky for 15 days tells a different story than one that appeared yesterday. And a triage queue. The highest scoring test on this list is tomorrow's stand-up item, not something that can silently accumulate. Test impact analysis is how you turn a 10,000 test suite into a 200 test suite for the average pull request. The flow has 4 steps. A code change comes in as a pull request, files added, modified, or deleted. A coverage map, which was built nightly from instrumented full runs, maps each line of source code to the tests that exercise it. The coverage map identifies the impacted tests, the minimal set that could possibly fail given the changed files. Selective execution runs only those tests and skips the rest. The payoff is roughly an 80% reduction in tests per pull request, which translates directly to faster feedback and lower CI cost. The coverage map is the key artifact. It's generated offline, cached, and queryable. One important guard. Always include a smoke test run on every pull request regardless of the coverage map. Coverage maps can have gaps, and critical paths should never be skipped based on an automated analysis alone. Here's the full picture of what good looks like, measured against a realistic baseline. Total execution time goes from 4 hours to under 30 minutes, achieved through time-based sharding across 8 workers. Worker parallelism goes from 1 to 8 to 16, enabled by containerized fixtures and isolated databases per worker. Flaky test rate drops from 5% to under 1% through detection, quarantine, and ownership. PR feedback time drops from 45 minutes to under 5 minutes through impact analysis and running only smoke tests on pull requests. False merge blocks go from roughly 2 per day to 0 by quarantining flakes and retrying once before reporting a failure. The bottom line numbers: 88% reduction in wall clock time, 80% reduction in daily CI minutes, 71% reduction in monthly cloud cost, and 9 times faster PR feedback. These are achievable numbers, not aspirational ones. Teams running these techniques regularly report results in this range. Today's challenge is to design and build a working slice of a 10,000 test orchestration system. The functional requirements are parallel execution across multiple workers, a sharding strategy that uses historical runtime input, flaky detection, and automated quarantine, test impact analysis for selective execution, and a comprehensive execution report. The non-functional targets are 10,000 tests in under 30 minutes, 95% reliability after quarantine, under 5 minutes PR smoke feedback, 0 false positive merge blocks, and 90 days of historical trend analysis. This is an advanced challenge. You're not expected to build every component fully in 3 hours. You are expected to make deliberate design decisions, implement the core sharding and detection logic, and document the gaps with a credible path to production. Your submission has 4 deliverables, each worth 25 points. The first is a CD pipeline design, a multi-stage YAML configuration with gating policies, retree behavior, and failure handling documented. The second is a parallel execution system, a working sharding implementation with workers, progress reporting, and graceful failure handling. The third is a flaky detection system, the statistical scoring algorithm, the quarantine state machine, and a dashboard design showing the promotion path. The fourth is an optimization results report, baseline metrics with evidence, the techniques you applied, measured or estimated impact, cost analysis, and remaining bottlenecks. Passing score is 75%. A production-ready submission that exceeds the 30-minute target with documented headroom scores 90 or above. To close, 4 principles to take away from this session. Stage by risk. Keep cheap and fast tests on every pull request. Push heavy and broad tests behind merge to protect review velocity. Shard by time. Greedy bin packing on historical runtimes delivers under 10% variance. It's the right default for most teams. Quarantine flakes. Don't mute them and don't ignore them. Detect, isolate, fix, and promote through a structured lifecycle. And run only what matters. Test impact analysis turns 10,000 tests into 200 on the average pull request. And that's where the biggest time savings live. Next month, we move to advanced performance testing. We'll cover load testing at scale, performance regression detection, and building performance budgets into your CI pipeline.